Welcome to the another session in Frontiers in CFD. So today we have the CFD simulation for thermal management of lithium-ion battery pack in a rectangular channel with air as a working fluid. So the today's objective is the preparation of geometry for the rectangular channel lithium-ion battery pack. Second thing is to generate mesh, do the name selection on the computational domain so as to apply the boundary conditions properly in the setup. And last thing is to visualize the result in post processor. So these are the reference geometry. It is taken from one of the reference paper. Instead of having this convergence plenum, we are taking the rectangular one at the top as well as at the bottom. All to the another session where we are going to do the CFD analysis on the thermal management of lithium-ion battery pack. The battery pack which is shown here in the screen will be following this battery pack, and instead of having the convergence plenum or the divergence plenum, will be having a rectangular kind of thing. So based upon that, we are going to just prepare the geometry here. So this is how the arrangement is there. So these are the dimensions that we are going to follow throughout the preparation of geometry in the design modeler, and we'll try to do the analysis. So this has been followed from one of the research paper. The dimensions are slightly different than the actual research paper, but and again, as I said, instead of convergence and divergence plenum, we have a kind of rectangular duct over there, and based upon that it has been created. So this is a bottom duct and this is a top duct. These are how the lithium ion cells, they are separated with respect to each other. So we'll go to prepare the geometry with the help of workbench. So let's start with the first thing, that is the fluid flow fluent. So there are various geometries are available for rectangular channel type of flow. So this is one of the arrangement which we are following over here. So let's open the fluid flow fluent. Okay, so first of all is the preparation of geometry. Open the design modeler. Okay, first of all set the units to mm because we are following this as the dimension here. So click on any one of the plane and just create a primitive, that is a box. So what should be the dimensions of the box? You can just see here. So dimensions of box will be 143 by 97. So we'll just prepare this first. Here it is, I will put x coordinate 143 and the z coordinate I will put it 97. This y component I will put it 65. So make it add to frozen and let's generate. So this is the one version which we have generated. Now accordingly we'll prepare some kind of duct arrangement on the above and below side for this. So before that we'll first prepare the primitive one more time. Say it is box over here. Now this box we want it as per the dimension. So z component will be as it is, that is equal to 97. X component over here, but it will be at the bottom side which is available here. So if you see the geometry again, that is 50 on this side. So your component which is in x and direction, that will be in the negative direction, that is x 50 and this is 143. So total will be your 193 over here. X component which is total is 93. Sorry, we'll put it, this is as it is. This is how much it is, 143. We'll put this is 143 here. Okay, let's take it 193 here. X component will put it minus 50. so it is be displayed here, and it is in z direction. So y component I need it 20 here, and this to be in minus negative direction, so I'll put it minus 20. So likewise it will be generated. So here let's make it add to frozen and then generate. So we have generated a kind of duct at the bottom. Similarly we'll generate a duct at the top. So we have created at the bottom, now we'll create at the top. So one more time, go to the primitive, put it in box. X component will be the same as this one. Put it 193 here on this side. Similarly y component will be 20, and this z component will be on this side, so it will be 97 as for this dimension. You can just follow, yeah. So put it will be like this, and it has to be shifted by up, so it will be shifted by y. So this is 97, so we'll put it, sorry, this is 65. I will put it 65 here, so it will be at the top. So in this way a duct kind of arrangement will be formed. Let's make it add to frozen and generate. So we have created duct at the top, we have created duct at the bottom. Now we'll make it unite so that there will not be any conflicts in the boundary condition. Okay. So we have done the unite operation for all these three bodies. So this is one single body which we are having. It will be like a fluid which is zone. So that's why I'm specifying this is a fluid zone. So you can put name here as a you can say a fluid zone over here. So this is the duct through which the fluid is been flowing. So this is a Boolean operation we are done. So fluid. Now next is the part which we are going to do is we are going to prepare the lithium-ion cells accordingly. So let's take the top view of it, and then one by one we'll generate the lithium-ion cells. So first of all, let's create a cylinder. Radius will be equal to 9, y component will be equal to 65, z component will be equal to 0. First x component will be equal to 14. Instead of add material, make it slice material. The z component here again it will be equal to 14. So let's make it generate. So this is the first one we have generated. So one more time, next one is primitive cylinder, make it slice material. So x component will be now as per the earlier one. So now it is 37 here, x component will be 37. This y component will be 65, this will be made as 0 here, and z will be equal to 14. So let's make it generate. So we have to do the slice operation over here. So one more time we'll create a primitive, that is a cylinder. Instead of add material, make it slice material. X component will be now is equal to this one, it will be 60. So put the value to be equal to 60 here. This one z component will be as it is 14 here, make this as a 65. This will be equal to 0, and let's make the generate the third one. So this is the third. Say one more time, create a primitive, that is cylinder, make it add to slice material. Now we took the 660, now it will be 83. X component will be 83, z component will be 14, this y component will be 65, and this one will be equal to 0. So let's make it generate here. So this is the fourth one. So total there are 6. So cylinder, add material instead of slice material. Now the distance is 106, so put out 106 over here. This will be 14 as it is, this will be 65, make it as 0, and let's make it generate. So one more time, create a primitive, let's say cylinder. Now the distance is 129, So put it 129 here. This will be 14 as it is. This will be 65 and this make it 0. Instead of add material, make it slice material and then generate. So this is how 1 2 3 4 5 6 are already generated as per the diagram. Now we'll generate the second and third and fourth layer. So one more time, go to the create as a primitive option, cylinder. So x coordinate will be okay, just a minute, this is 65, this will be 0. Now x coordinate will be equal to 14 here, z coordinate will be equal to 37. Let's make it slice material and generate. So as per the dimension we are following. So next one is create, say, primitive, that is cylinder. So here x coordinate will be equal to now 37, z coordinate will be equal to 37. Instead of add material, let's make it slice material. So put this to 65, let's make it 0 and let's generate. So this is the second one. Similarly, go to the primitive, that is cylinder. X component will be equal to 60 now. As per the dimension, x component will be equal to 60. This will be equal to 37 and make it slice material here. This made it 65. This component will be equal to 0. So this one. So let's generate the third one. Next cylinder. Instead of add material, put it slice. Now it is 63. Now it is 83 now. Then this is 37 as it is. This will be 65 and this will be equal to 0. So let's make it generate. So this is generated. So create primitive cylinder. Now it is 106. So put it 106. This will be 37 as it is. Instead of add material, make it slice material. This is 65. This is equal to 0. So let's make it generate. So one more time, create a primitive, that is a cylinder, make it slice material. So the dimension now is equal to 129. So put this is equal to 129. Z coordinate will be equal to 37 as it is. Make the x component is 65. This one is equal to 0. Let's generate. So we have generated two such rows. One more time we'll go with the next row. Cylinder as slice material. X component will be equal to 14. This one will be equal to 60 now. This will be 65. This will be equal to 0. Just check with the dimension. So third will be 60. So accordingly we are done for it. Let's make it generate. So one more time, just create, say, cylinder. Instead of add material, make it slice material. So here it is 37 now. 37 now. And this will be also 37 here. Make the y component to be equal to 65. This one equal to 0. And let's this where's on. Okay, just a minute. Where it is. Okay, this one, so you have to take it 60. Okay, second one, yeah, this will be equal to 60 here and make it generate. So it is generated here. So one more time, create a primitive, that is cylinder. So this third one will be 60. Yeah, it puts this as 60. This will also be equal to 60. Instead of add material, make it slice material. Take y component 65. This one will be equal to 0 and make it generate. So one more time, create a primitive, that is cylinder. Let's say x component will be equal to 83 now. This z component will be 60 as it is. This will be 65. This will be equal to 0. Instead of add material, make it slice material and generate. So ensure that each and every cylinder which you have generated, it should be sliced. Next one more time, this slice material, x component will now be equal to 83. Sorry, this is the fourth one. Now it is fifth one. It will be 106 here. 106, and this will be equal to 60. Y component will be 65. Make this equal to 0. Let's generate. Yeah. So one more time, create a primitive that is cylinder. Instead of add material, make it slice material. This is 129. Put 120. Sorry, 129. This will be equal to 60. This component will be 65. Let's make this equal to 0 and let's generate. Okay, so we have completed the third row. Now we'll generate the fourth row. One more time, make it slice material. X component here will be equal to 40. This Z component will be equal to 83. This will be equal to 65, and this one equal to 0. So let's make it generate. One more time, this one primitive, that is cylinder. Here as a slice material, X component will be now equal to 37. Z component will be equal to 80. This one will be equal to 65. This will be equal to 0, and make it generate. Sorry, no, 65. Sorry, 83, I guess. Yeah. Now let's move primitive, that is cylinder. X component will be equal to now 106. Here put it 106. Sorry, just on it. The third one we are dealing. 14 is the. Okay, so let's put it to 60 here. Y component to 65. Z component will be equal to 80 as it is. This will make it as 0. Instead of add material, make it slice material and generate. So this is 83, sorry. Yeah. Now next one, create primitive cylinder. Instead of add material, make it slice material. X component will be equal to the fourth term, that is 106. So make it 106 here. Z sorry, 83. Yeah. Then this is 83. This make it 65. Let's make this is equal to 0, and let's generate. Now one more time, cylinder, say 106 over here. Instead of add material, make it slice material. Z mob will be equal to 83. Then this will be equal to 65. This will be equal to 0. Let's make it generate. So last one, this is 129. This will be equal to 80. This will be 65, and this last one will be equal to 0. Instead of add material, make it slice material and generate. So we have generated all cells over here. Okay, let's make it 83. So we have generated all cells. Ensure that they are all done with the slice operation. Slice, just check it. Each and everything is related to slice as far as the cylinders are concerned. Okay, so now this is done. You can just visualize the geometry, how it looks like. So we are providing the inlet here and outlet here, and accordingly we are going to do. So now it is fluid zone, then this is cells. So we'll rename this as one by one as the cells. So this is the first, okay, second, third, fourth, fifth, sixth, 7, 8, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So these are the 24 cells. I will form a new part, let's say, and denote this as a cell here. At the same time, rename this, okay, this to solid, because okay, so everything should be solid. Just check it one more time. Yeah. Now rename this all to cell. So write down each and every name that is related to your cell. To avoid the conflicts in the boundary condition or to have a better understanding, it is important that you should rename this so that there will not be any confusion when you apply the boundary conditions. So put it cell over here. So let's make it cell. The last one, let's make it cell. Okay, so all of them you are define. This is fluid zone, and second one your cell. So fluid zone is actually solid, sorry, cell are solids, the fluid zone is your fluid. Now this is a part which is over with the generation of geometry. Now let's go back to workbench window and save the work. Let's go inside. So we have, this is, so 24 cell cooling with air duct. So 24 cell with airflow. Okay, so yeah, save the work. It's important to save so that we can access it later on. So let's proceed with the next part that is related to your mesh. So meshing is important, and simultaneously how you are giving the name selection over there, that is also important so that we can apply boundary conditions later. So let's generate the default mesh as per the understanding of your computer. If you want, you can further modify it also. If you find it somewhat not good, in that you can definitely modify it, but as of now I will put it this one by default as it is. If I will try to generate the result first, and then we can modify the mesh size so as to reduce the time required for simulation. So let's define the inlet outlet. So this is your inlet, this is your outlet. Okay, so fluid zone I will keep it hide. You can check the mesh size on this. Yeah, as I said, you can change the mesh size also. So let's select, okay, let's select all, because we need to apply certain boundary conditions here. Yeah, so select all walls. So go to the create name selection, I will put it cell wall. Yeah, now let's show all bodies. So you'll be having inlet, outlet, and your cell wall. So likewise the three things will be available. May just make it update. You will see the mesh translation to Fluent was successful. So inlet, outlet, and this is your cell wall. So these are the three things we are done. If you want, you now can close the meshing. So let's go to the setup part. Here click on edit, put it double precision, depending on how many cores you have you can select that. I put it around 10. Just close the browser. Yeah, I will close the file also. Okay, so let's wait to load the geometry. Yeah, so click on this. Okay, put it transient, specify gravity in negative direction, that is minus 9.81, because this is positive. Okay, now let's proceed transient, because energy temperature will be involved, so let's make it transient. Let's go to the model. I will select the energy equation over here because temperature variations are taking place. Then I am taking select viscous K epsilon, enhance wall treatment, thermal effect and curvature correction. Let's make it okay. Yeah, so now let's move to the boundary conditions over here. So we'll put some boundary conditions at inlet. Okay, sorry, one thing is left, material. Okay, let's go to the material. I'm using air as over there, but in addition to that, I'm selecting one solid, that is nickel, because the outer layer of the battery is normally covered with nickel. So close this. So you have nickel over here. I will keep air as working fluid by default. I'm not going to change it. So let's put some boundary conditions at inlet. I will put the velocity, let us say, is equal to 1 meter per second at inlet. Make it apply and then close. So this is one thing which is we are done. Then we don't have to do anything with the outlet. There are too many wall boundaries and conditions are available. So in that case, out of which we have to look for the cell. So we have 24 cells. Accordingly, we have to put the temperature at each and every cell. So we'll see this cell wall contact here. So I'm going to put the temperature on this cases. So it will take time, but we need to put it for all. So let's temperature, let's say is it 3, putting 333 Kelvin, make it apply, or yeah, put nickel and make it apply. So this is the first one, we are done. So one by one we have to do it for all. So let's take it temperature, let's say 333. Let's select nickel, make it apply, then close, apply and then close. So likewise you have to do it for all. The temperature, let's say 333 Kelvin, make it nickel, make it apply and then close, make it apply and close. Temperature, let's say 333 Kelvin, nickel, make it apply and close, apply, close. So this is some tedious task to do, but we have to do it for all. This is 33. Let's select the nickel, make it apply, close, make it apply, close. By mistake, if you forget any one of them, you will not see the temperature available in the animation window. So you need to you need to carefully do all these things. And there are total 24. So the number of cells increases. Your boundary conditions will, the one which you want to apply will also increase. So that may consume a long time in this process. So let's take it one more time. Make it nickel. This is temperature. Let's put it 333 Kelvin. Make it apply and then close. Make it apply and then close. Let's say here. Edit. Temperature. Let's say 333 Kelvin. Make it nickel. Make it apply and then close. Make it apply. So they might not be in range in regular pattern, because you will see they are arbitrarily specified it over here. Arbitrary in the sense like 17, 15, 16 now comes to like this. Depending on the position of cell, I think it will come in the random manner. So let's make it nickel, apply, then close. So let's go with this one. Temperature, let's put it 333 Kelvin. Nickel, follow, then close. Make it apply, close. Next one, this here. Temperature, put it 333 Kelvin. Nickel, apply, close. Make it apply and close. Few of them are remaining. So you could have done with the finer mesh size also, but I will just check out with how the simulation proceeds, and if it is satisfactory we can go back and define the mesh again, and we can update the solution. So that is one way of doing it to reduce the time which is required. So at least for the trial run we should understand whether the simulation is going in the right way or not. If it is going in the right way, you can definitely go on to update mesh size. If you update it at the initial stage, what will happen, the simulation may take time, and you may say putting a comment whether it is right going in the right way or not, so it can also take time. So that's why I put it comparatively a default mesh which is generated by computer, but definitely you can change it to the requirement as per your case. So let's put it 333, make it nickel, make it apply, close, make it apply, close. So few of them are remaining. Let's make it here. So this can become a long video because boundary conditions, preparing geometry, it takes time. Yeah, but I don't want to skip anything out of it, so that's why it's becoming long. This is 330, this is nickel, put it here, then apply and then close. Okay, last 3 4s are left. Temperature, this is 333 Kelvin, make it nickel, make it apply, close, apply, close. One more time here. Temperature, let's say 333 Kelvin, nickel, make it apply, close, apply, close. Okay, only 2 are left. This is 333 Kelvin, make it nickel, make it apply, close, make it apply, close. The last one. Edit. Temperature, this is 333 Kelvin. Okay, you can put your own temperature. I have put it 333, but as per your requirements you can put it. Okay, so we are done the boundary conditions at each and every place. We are not going to do anything at the outlet over here. So this is how the boundary condition. If you are having a different kind of material, accordingly you can specify different material also. So go to the reference values, tell the computer from where to start. Inlet. Reference zones, you take it, select the reference zone. This is fluid zone. Yeah. Then go to the initialization. Again tell the computer from where to start. Let's say inlet. Make it initialize. Yeah. So once initialize is there, go to the calculation activities. Put this around 20, so that even in the case of power failure, the system will save the work. Then go to the solution animation. So what we want to visualize, that we can check it here. So I want to visualize temperature, more specifically the total temperature. Yeah. Select all, go to the color map. Instead of exponential, put it float, make it apply, close, save display, close, select the contour one, make it okay. So this is how things are there. I'm just going to go with this the fixed time steps only. Just put it 100. And let's see at 1. If you get the problem of current number, you have to change the time step size to smaller one. But just for the trial run, I'm keeping it 1, and I have taken fixed time as a, instead of adaptive time step, I have put it as a fixed one. So let's visualize the things. Yeah, it's if you see the variations in the color contours, especially in your the total temperature, if you see that, then definitely what you are done is in the right way. Yeah, definitely you can see now the variations which are taking place in terms of the temperature is increased. You can see on the left hand side on your legends. At the same time on the uh, we say the duct which has been specified over here, the changes in the temperatures are observed, and that results that we can say that when the fluid has been flowing through these the packs, lithium ion battery packs, it is taking away the heat from the lithium ion battery pack, and the fluid is coming from inlet and it's going towards the outlet. So you can see the variations in the color contour. That variations in the color contour is actually the heat is taken up by the fluid from the lithium ion cells. So you can run it to a longer iterations, but definitely sometimes if you take as a fixed time step and time step size of 1, there are chances that the problem of Coron number can happen. So if you are getting the problem of Coron number, you definitely have to go with the either adaptive time step as well as you have to reduce the time step size. So these are the few things that can be done as we are doing just a trial run. So mm, as of now it hasn't come, so it may come. So on the safe side you can put the time step size to a lower value. So you can see some red zones over here. uh, this you can see at the bottom the flow time is around 10 yeah 10 seconds, and you see some hot zone also that is extremely on the left as of now, which is slightly rising upwards the red zones. So that is how the heat is being taken up by the fluid which is flowing from the lithium ion cells. So you can see the detailed views in the next part that is related to your result. We'll check out how the once the iterations are completed, we'll see these things in the post processor. So we are just run it around for 100 time steps, so it might take less time, but if you take it with a time step size is smaller, the time required will be more. So what are the difference of temperature which is there for air at inlet and air at outlet? So that will help us to know how much of heat is been taken up by the air when it is in contact with the lithium ion cells. So I have actually put some higher temperature over, that is 333 Kelvin, so as to visualize in quite better way, somewhat fast manner. So that's why if the temperatures are less like 313 Kelvin or 323 Kelvin, you can put that also. So you can see the color contours are getting developed. Red zones are quite getting advances when towards the right. The temperature which I put is slightly on the higher side. So once this is completed, we'll move to the post processor section. It is around 73%. Okay, the time requirements will be depends on your computer also. It's and how the mesh size you are selected. So as of now we have taken the default mesh size, so that's why time requirements are slightly lower on the lower side. But definitely you might be looking for the mesh which is somewhat fine, so as to have more accurate result rather than the mesh which you have selected. So this is all selected just to reduce the time required for the simulation. Now what has happened, we come to know the simulation is going in the right way. We definitely can go back to the workbench window and open the mesh again, and we can modify the mesh size and we can update the project. So that is how things can be done. So how this can be done, you can open the mesh through this here, and once you updated the mesh you can update the project. So likewise it is working. So this is now just now on the completion over here. you will see one message that is calculation complete. Click on it. Okay, so click on this, calculation complete. Go back to your workbench window, click on save project. It may take time depending on the size of the file which we are having. Yeah. Okay, if you want, you can keep it open, or you can close the Fluent window and open the post processor. Sometimes it shows the license issue, so it may be option of closing it. Okay, so let's go with the volume rendering here. Then put temperature as a one of the parameter. So here I will put it user specified, say around 298 to, let's say, 333. Put it here. I am just putting it with very low resolution as of now, but you can put it to higher also. Let's say take it 150. Will be quite smooth than what it is visible now. But again, the time requirement will be more if you go with the higher resolution, the one which is specified as 150. Contours will be quite smooth if you go with, yeah, just like now you can see the contours are quite smooth over here. And okay, so if you want, additionally you can put the streamlines also. So in streamline, use the variables as temperature here, start from, let us say, inlet. It may put it somewhere on higher value, should be on the higher side. Let's say it's 200. Make it apply. Yeah, now you can, I will just volume rendering I will close and just visualize the particles over here. Instead of time step, sweep animation, select this one, make it slow, and just see the particles how they are coming. They are interacting with the cells, they are taking heat from the cell, and they are leaving outside. Okay, so likewise the simulation can be visualized. I will just put it again to the volume rendering. Sometimes the system may get hang when you press on this button. Okay, let's have the volume rendering again, and again you can visualize the particles also. So likewise the things can be here. Just visualize it one more time. Okay, before that I will put the legend here. So appearance I will put it fixed, and number of value ticks I will put it 11. This aspect ratio I will change it to certain extent so as to have better visualization. Make it okay. So now it's quite better way. Let's go to the sweep animation one more time and just play it. You can see the particles, they are interacting here, taking the heat, and they are going ahead. So this is how the simulation that can be obtained. Once you click on the stop button, it will still go on to run till the time the last particle comes out of it. Okay, with the help of text you can put your name over here. Say here I will put it file name. So whatever the location you want, it's to be right, and this is to be center. Make it apply. So you'll see this one. In this way the simulation that can be visualized. So this is all regarding to the geometry which we are discussed earlier, and based upon that we are trying to do. You can change this duct as a convergence kind of thing and a divergent kind of thing. We have done it for rectangular, but it can be done for this kind of structure also.